AP Chemers. Today we're going to talk about separation of mixtures. So there are many different ways to separate mixtures. A lot of these we've talked about last year, but there are a couple of new ones. And just a reminder that a mixture is two or more pure substances mixed together physically, and so you separate them also physically. So no chemical reactions required in order to separate mixtures. So the first way we're going to talk about is direct separation. And direct separation is kind of like a broad term. It can involve a lot of different things. For example, if I have oil mixed with water, I could separate those by either, they don't dissolve in each other, they don't mix. So I could pipette one of the layers out, or I could use a separatory funnel to separate them. If I have yellow and red wooden balls, I could physically grab the red ones out. If I have a mixture of iron and sulfur, I could use a magnet to remove the iron. And so, again, direct separation is very broad. If you are using direct separation, you kind of have to be a little bit more specific about which of the direct separation methods that you are using. Next is filtration. So filtration is good if you are trying to separate mixtures of a solid and a liquid where the solid is not soluble in that liquid. So for example, sand water or silver chloride in water. Silver chloride is not very soluble in water. So what you do is you take your mixture and you get a funnel and you get some filter paper. And what you do with the filter paper is you fold it in half, and then you fold it in quarters, and then you pull out one of the sides like this. So that kind of looks like a cone. And then you put that in your funnel. Now, it's not very stable, so what you do is you get a little bit of whatever solvent your solution is in. So if what I'm trying to filter is silver chloride in water, I take a little bit of the water and put it here, just a few drops to make it stay. Then I take my flask with my mixture, I swirl it, and then pour it very quickly. And the liquid will fall through and the solid will remain on my filter paper. A lot of times when I do that, there's still some solid in my flask. So what you can do is use a little bit more of the solvent, swirl it around, pour it fast, and you can do that a couple of times in order to get it all out. Now, once all the water goes through, or all the solvent goes through, whatever your solvent is, then you take out your filter paper, and you usually want to dry that. You can let it air dry, which will probably take like a whole day, or you can put it in the oven to let it dry so that you can make sure that all the moisture and all the liquid has evaporated off before you mass this. And a lot of times you gotta heat it up, mass it, then heat it up again, mass it, heat it up again, mass it. You do that a lot until your masses are consistent. That way you know that you've driven off all the water. So that's filtration, solid and liquid, where the solid is not soluble in the liquid. Well, what if your solid is soluble in the liquid? So then you would use evaporation. And there are two different ways to use evaporation. You can heat up the mixture to get it to evaporate pretty fast, or you can just let it sit at room temperature. It's going to take longer, but for some mixtures, that's kind of required. For example, last year you did your gunk, and you had salt in water, and so you boiled the water in order to evaporate. You boiled your mixture in order to evaporate all the water out, and you end up with the salt. That would be a good method to separate salt from water. But what if you had sugar water? That would not be a good technique. You still want to evaporate it, but you don't want to boil it. You don't want to heat it because, sugar and water caramelizes basically. So you would want to let it sit at room temperature as opposed to heat it. So be careful when you're talking about evaporation, whether you need to apply heat or not. The next method of separation is distillation. And sometimes it's called fractional distillation because you get little fractions. We didn't really do any distillations last year, but we did do a demo. So a distillation apparatus has a round bottom flask. That round bottom flask is connected to a condenser. This is called a condenser here, which is made up of two tubes. The inner tube is connected to your flask here, and then there's an outside tube with water running around it. And the water does not touch whatever's inside of the inner tube. So what you do is you take your mixture, which is usually in the liquid form. So this could be different liquids together, or it could be solids and liquids mixed together. But the key is they have to have different boiling points. You take your Bunsen burner and you heat up your mixture. And the key to this is you have to do it very, very slowly. You want your temperature to rise very, very slowly. And the idea is as you hit the different boiling points of the different components, these components start boiling. And so they boil at different times and collect at different times. So as you heat this up, when the boiling point of the first component, so the component that has the lowest boiling point, when we reach that temperature, that component will start boiling and turning into a gas. The rest of my mixture will remain in the liquid form because we haven't reached its boiling point yet. So the substance, again, with the lowest boiling point is going to boil first, turn into gas. The gas will travel through this tube, so the inner tube. Now, the outer tube is connected to cool water, running water, usually connected to the faucet, and then the other end goes into the sink. And so that cool water cools down your hot gas that's inside and condenses it. That's why this is called a condenser. When it condenses, turns back into a liquid, and so you have a beaker here to collect that liquid. And the idea is you collect a little bit of this liquid, then you change beakers, get a new beaker, collect a little bit, get another beaker, collect a little bit, and so on. And the hope is that we did this slow enough that we are able to let each component with a different boiling point boil separately, and then therefore condense separately. A lot of times when you do a distillation, it takes hours and hours. And even when you're done with the distillation, sometimes if you look at your beaker, sometimes it has two different components in it. So then you do another distillation with those two components. So it's kind of a very long process. Crystallization is another method to separate mixtures. And usually this is if you have a solid that is a little bit impure and you're trying to get the impurities out. You typically won't encounter crystallization until your second year of college when you take organic chemistry. I'll very briefly talk about it, but I don't think it's something that you need to focus on too much. So let's say I'm in the lab and I make some caffeine solid, but this solid is not very pure. If I want to purify it, what I do is I take a solvent where caffeine is a little bit soluble in, and I heat up my solvent. So let's say caffeine dissolves in water, slightly dissolves in water. So then I take some hot water or hot whatever solvent, and I add it drop by drop to my solid, and I keep stirring until I add just enough to get it to all dissolve. So I'm basically making a supersaturated solution because my solvent is very hot, and I'm adding just a tiny bit just until it all dissolves. Then I let it cool down. Sometimes you can let it cool down slowly. Sometimes you have to aggravate it a little bit, like put in an ice bath or scratch the inside of the test tube or something like that. And when you disturb the supersaturated solution, it crystallizes. And so when it crystallizes, the caffeine will form these nice crystals, and any other impurity will remain dissolved in my liquid. And then you can filter that out. So that's a method that, again, typically they use in organic chemistry. The next method is chromatography. And chromatography is a big deal on the AP exam, especially paper chromatography. There's all kinds of different chromatographies. There's gas chromatography, HPLC, column chromatography, paper chromatography. And most of the questions that I have seen are about paper chromatography. And these have been, again, like very popular on the AP exam. So we're going to spend a little bit more time on chromatography. So chromatography is used as kind of like a detection method as opposed to like a separation method. So if I have a substance, and I don't know if this is a mixture or a pure substance, what I can do is I can run paper chromatography on it to see, is it made up of just one pure substance or multiple substances, so it's a mixture. The way that it works is you have a stationary phase. So in paper chromatography, that stationary phase is the piece of paper. And you can use filter paper, you can use chromatography paper. So I have a strip of chromatography paper here. That's called the stationary phase because it doesn't move. Then you have a mobile phase, and that one obviously moves. The mobile phase is basically a solvent. So let's say that I have, I don't know, like some green ink, and I'm trying to figure out, is green ink just one substance, or is it a mixture of different substances? So what you do is you take your piece of paper, and you draw a line with a pencil. It's very important that you use a pencil, not a pen, because the ink will actually mess up your results. So you draw a line with the pencil like a centimeter or two from the bottom of your piece of paper. And then what you want to do is you want to put a tiny, tiny, tiny drop of your mixture on that line. So you could use, there are things that are called spotters. You could use a toothpick. So for my ink, I got a tiny toothpick and I dipped it in my ink and then I dipped it on my paper and I made a tiny, tiny spot here. The smaller the spot, the better in chromatography. You let it air dry. It's important that it's not wet. And then what you do is you take a solvent that this substance or substances are soluble in. So I'm just going to use water. So you can have a chromatography chamber or you can just use a beaker. So I have a beaker and I put a tiny bit of water in here. Now, this is key that your liquid level should be lower than where your line is. And then you put your piece of paper in here and you usually like hang it up with, whatever, a stir rod or something like that. So we typically in our classroom just use a wooden stir and have it hanging like that. And when you do that, when it goes in the water, capillary action is magical and it makes the water travel up through the paper. Now, again, it's important that the water level or the liquid level is below that line. The reason is if it's above the line, then the water will, because this is soluble in water, the water will mix with it and it's just going to dissolve in my liquid here and nothing will happen, right? So I want it to be below and you kind of let it sit like this. And when it gets close to the top, when the water, you can kind of see the water level. When the water level gets close to the top, you want to take it out and immediately mark where that waterfront was, where the water traveled to. Okay, so I have one from before, and it looks like this. Now it's streaky a little bit because I didn't really let it dry very much before I started it, but this was green ink, and you can see that there's a blue spot right there, and then there's like a yellow streak here. So that tells me that my green ink is actually made up of two components, the blue and the yellow. So that's one way to figure out if it's made of different components or not. You can also, if you're comparing this to a set known substance, like let's say I'm trying to figure out if this mixture had caffeine in it. What you could do is you could calculate something called the retention factor or RF value. So let's take a look at that. So the retention factor is equal to the distance that's traveled by the component divided by the distance traveled by the solvent. So the reason why the substances in your mixture will travel different heights, like as you saw in here, the blue didn't travel as much as the yellow traveled further, is because of polarity and attractions between the solvent and my substances. So it looks like the yellow dye is more attracted to the water and therefore traveled with the water. As the water was traveling through the paper, the yellow traveled with it more. Whereas the blue, because it's at the bottom, did not have as strong attractions with the water, so it only traveled a little bit. It wasn't as soluble in it. And so if you look at this here, this is initial. So there's where I spotted my mixture, and there's the solvent, which is the mobile phase. This is the paper, which is called the stationary phase. And after you put this in your chamber with the liquid, with the mobile phase, after it develops, this is the chromatogram that you get. Chromatogram is like the piece of paper after it develops. So it looks like this mixture was a mixture of 3 components, because you can see 3 different spots now. And the top spot, that's the one that's the most soluble in your solvent, and it's the most attracted to your solvent. Remember intermolecular forces? We'll review that a little bit later, but again, the most soluble, the most attracted to the mobile phase will travel the most. The one that traveled the least would be the least soluble, or the least attracted to the mobile phase. And so again, what you can do is calculate this RF value, and as long as you have the same substance and the same solvent, even if it's on different chromatograms, even if you run at different times, you should get the same RF value for the same substance with the same solvent. So what you do, let's say I want the RF value for my lowest point here, my lowest spot. So I measure the distance that that spot traveled. So from where this line is to my spot, divided by the distance traveled by the solvent. So from where the line is to the line of the liquid up here, which was water in this case. And you divide those. It's a ratio, basically. So let's say, for example, caffeine will travel half the distance, so it would be 0.5 as the retention factor, and so on. Again, that retention factor is going to be the same. The ratio is going to be the same. The distance traveled won't be the same, but the ratio of them will be the same for the same substance in the same solvent. Okay, so just to summarize, chromatography, especially paper chromatography, has a liquid phase and a mobile phase. It has to do with detecting whether your substance is pure or a mixture. So if this was pure, you'd only see one spot here, and you can identify what the things are from this RF value. Another type of chromatography, there's different types of chromatography, but another one is column chromatography. Now, again, this is not something that I've ever done until grad school. So I don't anticipate you seeing this on the AP exam. However, in the CED, which is like your curriculum, it mentions column chromatography by name, but I've never seen a question about it. So I'm just going to talk about it briefly, just in case it shows up. So a column is, it could look, different, but this is a very small column. It broke, there was a tube there, but basically it's kind of a glass tube with a like semi-porous membrane right here. And what you do is you get a little bit of silica gel, which is like a powder. You add a solvent to it, make a slurry, and pour it through here. And then you take your mixture. So let's say my mixture is purple mixture. So I took some red dye and blue dye, mixed them together, made purple. So you add your mixture here, and then you keep adding solvent. And as the solvent goes through, your silica gel is your mobile phase, your solvent is your mobile phase. Sorry, did I say that backwards? The silica gel is your stationary phase. The solvent is your mobile phase, the one that moves. And as your solvent goes down, because of gravity, of course, it takes that mixture with it, the different components, and the one that's more soluble in your solvent is going to go down first, and the one that's less soluble is going to come next. And so let me show you this here. So there's my empty column, and then this is, I poured the silica gel slurry right here, and then you add some solvent to it, and then you add, there's your purple mixture, right? And you keep adding solvent and adding solvent. And as you add the solvent and the solvent runs through, you'll see that it looks like the red is more soluble in my solvent than the blue. And so you keep adding it until finally the blue comes out. You kind of collect it. And then after a little bit, the blue comes out. So that way you can separate the two different dyes. So that's just a brief overview of column chromatography. Last one we're going to talk about is centrifuging. If you've taken AP Bio, you've probably used a centrifuge. Usually they use it for like blood, to separate different components of blood, I think. But Centrifuging helps separate different substances by densities and also by size of the particles. So if you take a suspension, it's usually pretty good with suspensions. We use it in AP Chem at the very end to separate, like let's say if you have AgCl that's not soluble in water and I want to separate that solid, I can filter it or I can centrifuge it. And basically what it is a machine where you put your test tube in there with your suspension, and it spins really, really, really fast. And when it spins very, very fast, the larger particles go down to the bottom and sink right here, and then the smaller particles stay suspended in your solution. So if I'm doing the AgCl with water, basically the AgCl will fall down as a precipitate. Sometimes a precipitate just takes a really long time to fall, so this speeds it up to separate them. Then you can decant it. So this is a brief overview of separation of mixtures. That's it for today. I will see you guys later. Bye.